Let's go over the formulas that you'll need to use to find the volume of a solid of revolution using disks or washers. A solid of revolution is a solid obtained by rotating a region in the plane about an axis or a line. We'll first go over the formulas for rotating a region about the x-axis. In our first diagram, we have a region that sits on the x-axis. When we rotate this region about the x-axis, we get a solid of revolution that has circular cross-sections called disks. The volume of this solid is equal to the integral of the cross-sectional area from x is equal to a to x is equal to b. This circular cross-sectional area A is equal to pi r squared, and the radius r is equal to y, so our area is pi y squared. The volume for this solid can then be found using this formula. V is pi times the integral from a to b of y squared dx. I found that it's just easier if you write the pi in front of the integral. In our next diagram, we have a gap between our region and the x-axis. When we rotate this region about the x-axis, we get a solid of revolution that has circular cross-sections called washers. Just like with disks, the volume of this solid is equal to the integral of this cross-sectional area from x is equal to a to x is equal to b. This circular cross-sectional area A is pi times the outer radius squared, this is the outer radius, minus pi times the inner radius squared, where this is the outer radius. Each radius is equal to y, so our area is pi times y out squared minus pi times y in squared. The volume for our solid of revolution can then be found with the formula V is equal to pi of the integral from a to b, y out squared minus y in squared times dx. Whenever you use disks and washers and you're rotating about the x-axis, you're always integrating with respect to x. Let's now go over the formula for rotating a region about a line y is equal to b. The formula is written in terms of the radius and can be used for any region. In the first diagram, the line that the region is rotated about lies above the region. Since r plus y is equal to b, our radius is r is equal to b minus y. In the second diagram, the line that the region is rotated about lies below the region. Since the line lies below the x-axis, b is negative, and the radius r is equal to y minus b. It's really helpful with this formula to know that y is the distance from the x-axis to the curve, and r is the distance from the curve to the revolving line. If you remember that, you don't need to remember the formulas for r. Now we'll go over the formulas for rotating a region about the y-axis. These formulas are very similar in structure to the formulas that we just looked at for rotating a region about the x-axis, but now the integration is in terms of y instead of x. In our first diagram, we have a region that sits on the y-axis. When we rotate this region about the y-axis, we get a solid of revolution that has disk circular cross-sections. The volume of this solid is equal to the integral of this cross-sectional area from y is equal to c to y is equal to d. This cross-sectional area is pi r squared, but now our radius r is equal to x. So the area is pi x squared. The volume for the solid of revolution can then be found by the formula V is equal to pi from c to d of x squared dy. In our next diagram, we have a gap between the region and the y-axis. When we rotate this region about the y-axis, we get a solid of revolution that has washer circular cross-sections. For this type of region, the area is equal to pi r out squared minus pi r in squared, where this is the outer radius in blue, and in purple, you can see the inner radius. So the area is pi x out squared minus pi x in squared. And the formula for the volume for the solid of revolution is V is equal to pi times the integral from c to d of x out squared minus x in squared, where x is a function of y, times dy. Let's now go over our last set of formulas. These are formulas that you can use when you rotate a region about a line x is equal to a. This formula is valid for any region because the formula is written in terms of the radius. In the first diagram, the line that the region is rotated about lies to the right of the region. Since r plus x is equal to a, the radius r is equal to a minus x. In our second diagram, the line that the region is rotated about lies to the left of the region. Since this line lies to the left of the y-axis, a is negative, and the radius r is equal to x minus a. It's helpful with this formula to know that x is the distance from the y-axis to the curve, and then r is the distance from the curve to the revolving line. If you remember that, you don't need to memorize the formulas for the radius. Since finding solids of revolution is complicated, just to make things easier, I've written down 5 steps that you can follow. You're first going to graph the given curves, and then find the points of intersection. In step 3, from the graph, you can determine the value for the radius, that's r, and then choose the correct volume formula. Then the last step is just to evaluate the definite integral. Let's now walk through 8 examples. I know that sounds like a lot, but each example is representative of one of each type of problem you might encounter.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.